That's that. Oh, that's that. Excellent. So we'll start off with the fact that there's going to be all kinds of stuff in this talk. There's way too much material in this talk, so I'm going to tell you in advance I will not be answering questions during the talk unless that I'm the person asking the questions. And sometimes I do that to myself. But I am around all week. You have plenty of time to corner me and ask bits and pieces about relativity, about networks, about coding style, about all kinds of stuff. So I am here throughout the week. We're going to have to go through this very fast. I will be talking about light speed and why it's relevant and why we care about it. If you want to get in touch with me, I'm on all the socials pretty much. You can find me in most places. But first of all, we need to establish what we mean by this term space-time. This is not a term I made up. It's a term that comes from the theories of relativity, both special and general, or rather it comes from a guy called Hermann Minkowski, who coined this term in 1908 to try and understand the fact that Einstein had come up with a fascinating theory of invariance related to time and space, effectively unifying them as one. We often think about these as two separate quantities. But as developers, you know that you often trade off space against time. You want it to be faster? Cache it. Okay? You want to use up less space? Don't cache it. Okay? Sometimes you want both. It turns out that there are limits to what we can explore here. So I'm going to be doing a bit of a journey through some of the theory, but let's talk about space-time. The concepts of time and three-dimensional space regarded as fused in a four-dimensional continuum. I am telling you this, one, as a help for the rest of the talk, but two, if you are looking for a more interesting introduction when somebody asks you, what do you do for a living? This vocabulary will help you. I develop software. No. I travel in space and time. I fabricate realities at the whim of other humans. I cast spells using symbols and incantations through pipelines of possibility. That's how you introduce yourself. Useful in visualizing and understanding relativistic effects, such as how different observers perceive where and when events occur. Okay, so relativity, this is all kind of Einstein stuff. Einstein, most famous equation in the world. Basically, this is a theory of mass-energy equivalence in a rest frame. Fascinating as this is, we are not interested in that, but we are interested in this. The speed of light. This is the speed of light. It's not roughly the speed of light. It's not approximately the speed of light. This is the speed of light in meters per second. It's the definition of the meter. So if for some reason the speed of light changes tomorrow, so does the meter. Okay? So there is this idea. This is fundamental. Of course, as developers, this is way too much. Just think of it as this. Okay? It's a lot easier. Now, a point that I want to make clear, because every now and then, because we are software developers, so sometimes we're a little bit pedantic. Every now and then when somebody says the speed of light is constant, somebody says, oh no, but it changes speed in a medium. No, when a physicist says the speed of light is constant, they mean the speed of light in a vacuum is constant. They don't say the rest of it because it's obvious. It's only software developers who point this stuff out. But software developers might have a small point. What happens when light goes through a medium? Okay? When it goes through a medium, it does effectively slow down. And when it goes from one medium to another, there is a thing called refraction. And therefore, basically, where the light speed is different. And the light speed is different in glass to what it is in air. And so therefore, you get an effect. And this is characterized by the refractive index, which is written as n. And effectively, what it says is the velocity in medium A, where you're coming from, into medium B, where you're going to. It's a ratio. Now, what has all this got to do with anything? Well, first of all, we need a vivid illustration of this. Well, there you go. Beautiful illustration. Okay? This is taken from the 1973 Pink Floyd album, Dark Side of the Moon. Now, of course, scientists generally come along and spoil things, don't they? That is the job of science, is to spoil all our fun. It actually looks like this if you do it as an experiment. So scientists are here to spoil all our fun, but the point here is that refractive index is a useful concept. Why? And you're sitting there thinking, when is he going to get computers? When's he going to start talking about software? Right here. The speed of transmission in air is c. We're not going to worry about any differences. In a wire, it's close enough to the speed of light. Let me be clear. The speed of a signal in a wire is not to do with the speed of the electrons. Electrons are actually quite slow by comparison. It's to do with the electric field, the electromagnetic impulse, so to speak. So we don't worry, I'm going to say it's basically equal to that. The slowest medium any message travels through is software. Yeah, software. What is the job of software? It is to slow hardware down. Yeah, that is your job. I've got this amazing piece of hardware, how can we slow it down? Well, let's put some processors on it. More frameworks. Yes, let's build a fuller stack. Awesome, that should slow it down. The hardware is really fast. Your job is to make it not as fast. So it's the slowest medium. Some of this speed loss is necessary, but much is not. Most software is wasteful of its resources, including time. So that means that we can consider networks and software systems as having a refractive index. In other words, you send a signal, and then it goes through software, it slows down. So what is the refractive index that we want to care about? Well, I want you to imagine a network. There are 2 points on the network. They're going to communicate. We are not interested in this because that's not in the network. Yeah? The whole point of a network is it shows you the paths of possibility. That is not a possibility. Okay. Oh, well, no, sorry. It is, but we call it hyperspace, and that's outside current physics. Maybe that's a talk for next year. This is the shortest route. That is the fastest route. Sometimes your messages will be routed like this. Why are they routed like this? Is it anything to do with the network topology? Is it anything to do with light? No, it's software that made that decision. Because light has no problem sharing signals with other signals. There is no problem there at all. It is to do with routers and how things are switched. And that is all software. And in fact, there's something else going on here. Every single node has a slowdown factor because it has, you guessed it, software. So therefore, even the most direct path is going to be slower. So the refractive index of this network is the ideal velocity over the actual velocity. That's hard to measure, but if we flip it around, the actual time over the ideal time, which you can factor out like this. The overhead, so the refractive index of a piece of software or a computer system is the overhead divided by the 1 plus the overhead divided by the ideal time. Or if that helps you think, what is the cost of software? Okay? So, next time you are thinking about physics and speed and all the rest of it, this is the way to think about it. But you don't want to know this. This is too low level. This is the physical layer. You want to move up the layer stack to stuff like IP or TCP/IP. Does anybody here actually program at that level as opposed to something on it? No. How about this one? Anybody programming at this level? Okay, a couple of hands going up. Anybody using SOAP? REST? Okay, then we're getting somewhere. We have a history of this stuff moving further up. We started with RPCs in the 1980s. Anybody using gRPC? If I hit a level where people, yeah, okay, we're getting there. So the point here is we're moving up here. Anybody working with services in the retro sense or microservices? Anybody working with microservices? Yeah, you're probably actually working with services because there's nothing micro about them. But, you know, if it makes you feel good to put on your CV, you just go with it, okay? Micro means small. I just want to remind you that. No, micro doesn't mean small. Micro means really small. Like really small. We normally deal in these. But a lot of people dealing with this stuff don't necessarily have a background in distributed systems. So we need to have a proper definition of what we mean by distribution. So a number of years ago, I co-authored this book, Patent-Oriented Software Architecture Volume 4, a pattern language for distributed computing. So we gave a definition of what is a distributed system. A distributed system is a computing system in which a number of components cooperate by communicating over a network. This is a perfectly reasonable and serviceable definition. It's not very exciting. I much prefer Leslie Lamport's definition. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Yeah? Feel familiar? Yeah, now we're on home territory. And this is the challenge. It turns out there's a bunch of things that don't work the way that we expect or want them to. So, let's go through a couple of things that we're going to explore. First of all, has anybody heard of CAP Theorem? I don't care if you're an expert in it, just have you heard of it? So a few of you have, okay. Has anybody heard of the fallacies of distributed computing? There's a few of you. You're in the right place here. Anybody heard of a note on distributed computing? This is kind of a classic paper. Okay, so you are definitely in the right place. Has anybody heard of ANSWER? Oh, there's about one hand. So ANSWER is the one people have never heard of, normally. Advanced Network Systems Architecture. This was an effort undertaken in the 1980s and early 90s as part of the ALVI program in the UK. Now, I did a master's degree in the early 90s where this actually featured, and so therefore a lot of the stuff that I learnt about distributed systems way back then comes from this particular project. You can now find it. It used to have almost no internet footprint at all until the Computer Conservation Society stepped in, and there's a whole load of stuff there. But there's a whole load of things. 1989, An Engineer's Introduction to the Architecture. This is really influential on a lot of thinking. It influenced a number of standards, things like that came out in the 90s and 2000s. The ISO standard for RMODP, Reference Model for Open Distributed Processing. There's a lot of stuff that influenced here, and a lot of the stuff that was going on in the 90s and 2000s benefited from it, but it wasn't necessarily that well known. So some people knew about it, a lot of people didn't. So I find this really interesting because a number of people, they arrived at the distributed computing message later. So let's start off with the stuff. This is one of the things I learned. I was actually doing my master's in 1991. I had a thesis on actor-based computation. But a lot of the stuff we cared about could be characterized from this. And one of the most interesting things that ANSWER did is that it described a set of negative assertions. I remember being presented with these as negative assertions. What do I mean by that? Well, it's important to identify explicitly the assumptions which are made for non-distributed systems. In other words, your regular coding. I'm writing a piece of code, it's in a single process, that's my default, that's where I learn, that's what the language, if you think about it, almost every language that you are likely to work with is a single processor language. Very few languages actually have a concept of other machines. You have to go to the library for that. But you don't have the idea of remoteness in the language. It's facilitated through just another library. So most languages are completely unaware of the existence of the outside world. And honestly, I think that's sometimes reflected in developers. So the point here is we need to challenge our assumptions and the defaults that we learn, the things that we see that are convenient on the screen that are actually not true. To ensure that these assumptions are absent from the models for distributed systems, and they describe this as, these are assumptions to be avoided, and they listed off 10. Single global namespace. Yeah, it's partitioned. What something's called over here may be completely different to what it's called over there. Related global shared memory. If I've got a pointer, I can't point over there. The pointer is localized to a single address space. Global consistency. This is going to be a biggie. The idea that whatever I know over here can also be known over there. A value, a piece of data, is not necessarily going to be globally accessible and synchronously known. That's why people invented transactions and all kinds of other mechanisms, because you can't guarantee everybody sees the same thing. Sequential execution. Yeah? So most languages have no concept of multi-threading at all. JavaScript has no idea. And you know what? Even Java and C# are pretty ignorant about it, because to launch concurrency, you need to use additional constructs that are library constructs. You can't see the concurrency in the language. If you look at the page, it looks sequential. Concurrent code is actually sequential looking. If you want to know what a parallel or concurrent notation looks like, look at music. That is how you write things that happen together. When I look at a piece of source code, it is sequential, even if the runtime is actually not. But a network is inherently concurrent. You can't get away from that. Total failure. The point there is that you can't assume you have total failure. What do we mean by that? Well, if an application fails, then it fails, and that's it. You don't have to worry about it. It's a bit like being at the center of a nuclear explosion. You have nothing to worry about. Yeah? It's the best place to be. Yeah? That's it. You're gone. There's nothing you go, ow, this hurts. No, there is no it hurts. There is no you. There is no nothing. The application crashes, that's it. The whole application is gone. In distributed systems, we have partial failure. Partial failure means one part is not running and another part is. Oh, the client is running, but the server's down. Okay? We can have partial failure, and that complicates things. Synchronous interaction is a kind of an extension of the sequential assumption. A lot of stuff is asynchronous. Locality of interaction, you can't assume that things are local, and therefore there is latency. Fixed location, things migrate. Also, network topologies can change. Okay, so therefore direct binding to something is not guaranteed. Whether it's a physical location or some other address, you can't guarantee that. And kind of an obvious one, but it's worth stating, homogeneous environment. Everything is running the same hardware and software architecture. That just simply doesn't apply. So, of these, well, total failure is one of the most familiar. This is my publisher. I published a couple of books through O'Reilly. Fire in California, can't read your e-book in Pennsylvania. Yeah. And this is important because there's a whole load of transparencies that we like about distribution, the ability to replicate, the ability to move things around, but it doesn't always work, and the failures are surprising. However, it is worth dealing with a myth here. One of the myths that I've been taught, and many people are taught, is this one. The internet was invented by the Pentagon and designed to survive a nuclear attack. Well, I know it wasn't invented by the Pentagon, but a lot of people think it was designed to survive a nuclear attack. Unless, of course, you're right in the middle, yeah, in which case you don't care about whether it survives. Technically, because it's decentralized, it does have a certain level of resilience. But that's not why it was designed. The truth is that whatever you wish to attribute to ARPANET, the forerunner of the internet, as regards the origins of the internet, it is clear the early internet was not motivated by considerations of nuclear war, but by a need for technical protocols to allow computers and their users to communicate. It's just a bunch of geeks. ARPANET was primarily an early computer science exercise rather than a military one. So that's myths. Let's move from a myth to a fallacy, or a set of fallacies, what are often known as the fallacies of distributed computing. These were originally coined by L. Peter Deutsch. His original list of 7 fallacies was the mid-1990s. It didn't really start escaping Sun Microsystems, where he was, until the late 90s and early 2000s. What is interesting is there is no reference here to any of the other research that had been done before. And it's interesting to the degree to which the wheel gets reinvented. So Bill Joy, inventor of VI, for those of you that are watching closely, and closely involved in BSD, Dave Lyon had already formulated a list of flawed assumptions about distributed computing that were guaranteed to cause problems down the road. So they had 4. The network is reliable, the first one. In other words, when I call something, the calling mechanism is there. When you call a method on an object in your own address space, you never worry about the fact that the object delivery mechanism might fail, the dot might fail. When I call object.method, you never wonder, what happens if the dot doesn't work? The dot always works. So I've had one person say, yeah, but Kevlin, sometimes you get an exception. Not from the dot, from the other method, or if there was no object there, if it's null. But you don't get it from the dot. We're basically saying the dot might not work. There was a rather good outage in the UK that demonstrated this one. Just before Christmas in 2018, one of the largest mobile suppliers kind of stopped working. Not good. Latency is 0. Yeah, it doesn't work. But people program as if it does. So, see this? See that? Have you ever had that oh shit moment? Where you go to something and it's your orders, your money, your stuff. You go into the app or on the web page and it shows you, you have nothing. Your heart stops and then a moment later you have stuff. It's like, why did you do that? Because the code sucked. That's why. Now, I'm not going to blame individuals because we don't know everything, but let's be really clear. A large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. In this particular case, draw out a state model. Most developers don't know how to do this, but it's really helpful. What you have is that somebody thinks when I create the screen, when I create the list, there are no things in it. Therefore, I will display 0. This is wrong. I cannot tell you how wrong it is. And then what you get is you get a loaded event. Now the data is loaded from the database, and now we have 3 things. This is not the correct way to do this. The correct state model is we are loading. The fact that length is 0 is true but irrelevant. There is nothing there to talk about. Let me just give you an example. Let me just demonstrate this dry. This is an empty cup. Yeah? This is not a cup. Can you tell the difference? Good. Same. We are loading. There is nothing there to talk about yet. What orders? There is no concept of orders at this point. Orders have not come into existence. We have an empty screen, not an empty collection. And then it becomes displayable, at which point you display it. Do not display it. And that leads to crazy code that looks like this. That is the correct way to do this. Do not give people that oh shit moment. Because what you did without realizing is assumed that there was infinite light speed, that the latency was 0. Trust me, it is not infinite. Which leads to the next point. Bandwidth is infinite. Sometimes people assume, yeah, I can just send everything. Let's be absolutely clear. Right, I live in Bristol. There is a brewery that does actually brew infinity. This is the only infinity you will find. Because there are no infinities in the physical universe. Let me be absolutely clear about this one. It's a mathematical concept. It's not a physical one. When a physicist says, oh, this becomes infinite, it's a polite way of saying, and our theory breaks down. Yeah, but they don't say, oh, yeah, it screws up here, our theory breaks down. They say, oh, it becomes infinite. Infinite is not a thing. It's not a number. It's not a thing that exists in physics. There is no such thing as infinity. Just remember that, except for the pub or the beer. When you come to Bristol, call me. The network is secure. Well, we know this is bullshit. Okay, so James Gosling, inventor of Java, had actually codified these 4, calling them fallacies of network computing. Now, Deutsch wrote the list by this time 7 items strong into a slide presentation. So, a couple of others. The topology doesn't change. Yeah, machines never move around. This was even said before mobile computing. They were considering mobile computing. But we know that even with laptops and everything, topology changes all the time. There is one administrator. So you have different, no, that doesn't work either. And similarly, there's this one, which is ambiguous, unfortunately. He never really wrote it up in detail. Transport cost is 0. That either refers to the cost of maintaining the network, as in money cost, or it's back to, guess what, stuff takes time. Gosling added the 8th fallacy in 97. The network is homogeneous. Yeah, we heard this one before, about 10 years earlier. I love the fact that this was the last one they added, whereas it's actually one of the most obvious. And that's because it is obvious. We forget. It's so easy. Many things that are obvious are things that we overlook. Now, a number of people have tried extending this. A number of people have said, oh, the original 8, we've gone and added a few more. I will say that almost every single one of them is not worth looking at. They are not relevant. They're not similar. Unless they come from answer, ignore them, with one exception, Peter Deutsch. Given that he codified it, he gets special permission to add the 9th. It's really an expansion of number 4. It extends beyond the boundaries of the physical network. The party you are communicating with is trustworthy. Yeah. Now, this is not just about bad actors. This is not just about people acting malicious. Remember CrowdStrike? Yeah, people send me failure screens. I got a lot of failure screen messages that day. Busy day for you, yeah. CrowdStrike were not trustworthy, even though their job is trust. They didn't do it because they were bad people. They weren't after your stuff. In fact, let's go back to that O2 outage in 2018. Why was there an outage that knocked out one of the major mobile networks in the UK? They forgot to renew a certificate. Oops. This leads to Hanlon's razor, which is phrased in various different ways. Never attribute to malice that which is adequately explained by incompetence or stupidity. By the way, this explains most politics. The point here is to be untrustworthy is not necessarily to be bad. People can be untrustworthy and yet have all the right intentions. So, yeah. So let's look at this other thing, a note on distributed computing. Now, this one fascinates me because a note on distributed computing was written in 1994. That's kind of the time that L. Peter Deutsch was putting together the fallacies of distributed computing. This was written by a number of people who work at Sun. Jim Waldo was one of the key architects of Java's RMI. L. Peter Deutsch was at Sun, yet there appears to be no transfer of knowledge or reference. I find this fascinating. The dynamics of large organizations are always interesting. And a note on distributed computing made a number of really good points. Again, re-emphasizing, there are fundamental differences between the interactions of distributed objects and the interactions of non-distributed objects. What they were highlighting is the fact that in the 90s, object orientation was becoming a more interesting and dominant paradigm. This is 2 years, or actually about 18 months before Java undergoes its first major release. Its alpha releases were the year after this. C++ was already a major force in terms of the employment market and coding. Microsoft's component object model was kind of very much the thing that people were talking about. Either they were swearing at it or they were swearing by it, but they were certainly talking about it. And interesting enough, if you actually look back through a lot of the history of distributed computing, things like RPC, they were intrinsically object-oriented. The ANSWER stuff was an object-oriented idea, but they were very clear to say this kind of object is not the same kinds of object that you use in your local process. It's not the same kind of programming. In fact, it's one of the reasons that I still harbor a basic dislike of properties on things like, if you're working with C#, I have a deep distrust of properties because they hide the fact that there is access. And I remember seeing this in a distributed language and thinking, this is absolutely terrible. Somebody said, this is terrible because it makes it look like a really simple assignment, or access does not have all of those issues, partial failure, latency, and all the rest of it. So there was that. The idea is that if you do have an object model, it's going to look different. Okay, it's a distributed object model should necessarily look different. And they said distributed object-oriented systems based on a model that ignores or denies these differences is doomed to failure. And you know what? A lot of people did that in the late 90s and early 2000s, the late 2000s, the early 2010s, the 2020s. People still there, oh, it's just objects. No, it's different objects. They have the paradigm is not identical. The constructs are familiar. Some of the thinking patterns are familiar, but you need to take into account, you cannot make everything transparent. And pretty much they end up restating what we already knew a number of years before. And it's a really important point. It's a point that Martin Fowler emphasized in Patterns of Enterprise Application Architecture in 2003. You can't just take a group of classes you design in the world of a single process and come up with a distributed model. Lots of people tried to. Their systems sucked. But you know what the good thing is? If you're a consultant, people having sucky systems is great. As somebody who is a consultant and a trainer, this is fantastic. So, you know, actually I'm doing the wrong talk, aren't I? Sorry, cut. But this is actually true. People make the same mistakes. We can't know everything, but the point is once you know it, you really need to pay attention to it. Which leads to Martin's First law of distributed object design, don't distribute your objects. Okay? And that's what he means. He doesn't mean don't use an object-oriented paradigm. He means whatever you think of as your default object style that your programming language gives you, that is not the way you do this on the network. It's going to lead you to chatty protocols. It's going to incur huge amount of wasted time. Now, it's not just a question of time. We also need to account for other factors. This is where we hit CAP. It was originally stated by Eric Brewer in 1999 as the principle. It then became a conjecture, and then it was proven to be a theorem. And the paper that proved it was published in 2002, Seth Gilbert and Nancy Lynch. It was phrased also as Brewer's conjecture or Brewer's principles, and the feasibility of consistent, available, partition-tolerant web services. So they framed it from the point of view of web services. Actually, the web service bit is irrelevant. This is to do with networks and data. When designing distributed web service, there are three properties that are commonly desired: consistency, availability, and partition tolerance. I will elaborate on these terms in a moment. It is impossible to achieve all three. This is, let's be absolutely clear. When they say it is impossible, they don't mean it's really hard. They mean it's not possible. Possible is a thing that can happen in the physical universe. This is not one of them. Yeah? All the things that can happen in the physical universe, no. Sometimes people, this is what I love about software developers, is sometimes the engineering mindset as opposed to the scientific mindset. The engineering mindset says, okay, so this is guidance. You're giving me tools and tips. No. In what way is this useful? I'm just telling you how the universe is. What you do with that knowledge is entirely up to you. This is not guidance. This is reality. Ooh. Okay, so let's go through these. Consistency. That means whenever I try and get a value, a data value, basically that's any data value, read or write. This data value might be a status on a social media platform. It might be your bank account, your current balance. The point is, something that is distributed, somewhere there is data. And I can read that or I can update it, I can write to it. Consistency says every single read operation will return the latest update or failure. You will only ever, if you receive something, it will be the most recent value. And so therefore consistent, everybody will believe when they've got that, it's the latest value. This is correct. Or, oh, I'm getting errors. But you will never have a different point of view to somebody else. Availability, you will always get a response. There is a success response. I will always give you a value. I will never give you an error mode, but it might not be the latest value. This is caching. You're looking at something that's a bit stale. It's a bit out of date, but you got a value. Partition tolerance. I always hate this term because it always deserves explanation. Really, it's just failure or tolerance. And had they just chosen tolerance, that would have given us the CAP Theorem, which is much more exciting. Partition tolerance, what does it mean? Okay, so here's a network. Okay, that's a network. What if I take this network and I knock out that central node? Boom, suddenly, oh, we have partitioned the network. That's what it means, okay? So you basically, your network has become a not work, but for the Russian speakers, it's a network. The whole point here is how does it so the point here about the CAP theorem is you can be consistent with partition tolerance. In other words, in the event of any failure, you will never get a wrong value, but you will get errors. Okay? Or we can have availability and partition tolerance. In the event of any failure, you will always receive a value, but it might not be the latest one. Or consistency and availability. Now, some people kind of say, oh, well, this is not an interesting category because networks always fail. No, it's a misunderstanding about CAP theorem. I mean, certainly consistency and availability applies to your single process applications. you can always have the right value, and you won't get an error, and it will always be you will always get a value, and it will be the right one. Is basically what that says. But in the event of failure, you're screwed. You get nothing. But actually, most of the time, when applications are working, they can be in one of each of these. This is not a system is a consistent and available system. It's this morning it was this, and then it broke down. Or rather, sorry, this morning it was this, and then there was a failure. And we made an engineering decision to favor availability over, say, consistency. That's where it starts guiding you, okay? You have to make a decision. But the idea is you cannot have all three. Now, The Hitchhiker's Guide to the Galaxy by Douglas Adams, which gave us the idea that the answer to life, the universe, and everything is 42. There's a wonderful scene in it that highlights you have two philosophers arguing that they demand rigidly defined areas of doubt and uncertainty. That is what the CAP theorem is. It's what's known as an impossibility theorem. It tells you the things that are not possible. It gives you a limit on reality. Speaking of cats, we have things like Schrödinger's cat, and this, funnily enough, relates to, this is Heisenberg's uncertainty principle, if you ever wonder what it looks like. But it basically says there's stuff that we cannot know. You cannot know the position of something and its momentum to high fidelity. The more you know about its position, the less you know about its movement. The more you know about its movement, the less you know about its position. There is a limit of what you can do. However, let's be absolutely clear. This does not excuse. CAP is what gives us eventual consistency. It gives us this idea of things. But here's something that this does not excuse. You probably experienced this. I get this one with a variety of apps. You have two orders, and it shows me a list of 3. It's just like, and I've had people say, oh, yeah, that's because we're using micro front ends. No, it's because you have a sucky architecture. Because literally in the same process, you have on the same screen, you are lying to me. Oh yeah, but the number came via a different data path to the actual items. Right, that's fantastic. And what did you do about it? The correct answer is this. No other answers are acceptable. This has nothing to do with CAP theorem. This has nothing to do with eventual consistency. This is everything to do with understanding that if you have 2 different answers, pick one, not both. The point here, it is a feature of a distributed system that it may not be in a consistent state, but it is a bug for a client to contradict itself. If you are in the same address space and you are giving me 2 different answers, that's on you. That's nothing to do with physics. That's to do with biology. Okay, so there is a corollary to this. This was put together, this was observed 2010, Daniel Abadi, the Passelt theorem. They just keep throwing the letters in there. You can see CAP in there. And what this was is, again, this is not really guidance, but it is showing you the space of possibilities. Because what Abadi noticed was exactly the same thing I highlighted, is that people get trapped into thinking our system must be one kind of variant of CAP. We must be consistent and partition tolerant, or we must be available and partition tolerant. Most of the time, your network does not suffer a partition. So Passelt was basically trying to understand the design space and possibility space, and it is a theorem, it was proven. So if your network is partitioned, you have a choice. You can either be available or consistent. You cannot be both. That's what the CAP theorem tells us. But if this is the E in Passelt, see what it's done, very clever. If your network is fine, then you have a different decision you can take. You have a decision to do with latency versus consistency. You can be completely consistent, but you can't do anything about latency. Or you can say, we wish to reduce latency, but there's a trade-off with consistency. And so that gives us a series of possibilities. And the idea is you need to work out where your code fits. So let's go back to latency. Martin Fowler, he wrote the foreword, that book I showed you on distributed computing that I co-authored, he wrote the foreword to that book. I've known Martin a number of years, and he knows to send me error messages as well. You ought to know that United may have discovered a kink in the time-space continuum. over the Atlantic, but sadly they weren't able to take advantage of it and get me home earlier. Time to destination, 0. Distance, over 2,500 kilometers. That would be amazing. That technology does not yet exist. Let's just understand that the total distance is 5,500 kilometers between Heathrow and Newark Airport. This is not 19 centimeters. This is 19 light milliseconds. This is physics. This is a limit on what you can do. Why am I saying this? Well, if you have a server in London and a server in New York, and let's say you're a bank, and somebody says, we need our servers to be in sync with respect to 10 milliseconds. They should never be more than 10 milliseconds inconsistent with each other. You can just put your feet up on the desk, break out the bourbon, or the whiskey, depending on which side of the Atlantic you're on, and just drink, because there is nothing you can do. Oh, but it's a customer requirement, and customers value. Doesn't matter. Because either it's not your problem because it's physics, or you have solved the problem and are waiting for your Nobel Prize. You don't need to worry about jobs. The point here is that this is a physical impossibility. But occasionally people do get asked to do things that are actually physically impossible, not just hard. So it's the reminder, the speed of light, which we represent by c. C is the Latin for celeritas, means fast. But there's also something else it stands for, causality. Turns out, although we're obsessed with light, it's actually the speed of causality. Causality is this thing happens and then it can affect another thing. And I'm going to return to Leslie Lamport, who we had earlier on as offering the definition of a distributed system as the failure of a computer you never even knew existed prevents you from doing work. Wrote this classic paper in 1978, Time, Clocks, and the Ordering of Events in a Distributed System. This turns out to be quite important. Again, he kind of highlights these issues which surprise us when we come from an ordinary standpoint, familiar with coding in our IDE in a process for a single space. In a distributed system, it is sometimes impossible to say that one of two events occurred first. The relation happened before is therefore only a partial ordering of the events in the system. This is a fascinating idea that you cannot necessarily uniquely determine the order, a total ordering for everything that happens in your system. Now you might say, well, let's use physical clocks. The problem is physical clocks drift. The clock on this server might be different to the clock on that server. You have a challenge of synchronization. And so what is interesting is that he explores this in some detail, but he makes a couple of observations which go back to all of the problems people keep reminding us. And the point is, we shouldn't be too hard on ourselves. I've kind of joked about it. We shouldn't be too hard on ourselves because sometimes you get so used to the simple view that's presented in the IDE, you forget that actually it's a lot more complex. You know, you might be working on a service and have a service-centric view. And internally to that service, perhaps the world is sequential and simple. But that forms part of a system. And it turns out the system does not look like what you're looking at all. It does not behave that way. And importantly, your programming language has no capacity to talk about it. So it's up to you. You need to remind yourself of this stuff. And your colleagues as well. This is why we use group intelligence in teams. We have found that problems often arise because people are not fully aware of this fact in terms of ordering and its implications. He defines the happened before relation formally. A happened before B means that it is possible for event A to causally affect event B. And of course, now that you're all experts in special relativity, this is good. This definition will appear quite natural to the reader familiar with the invariant space-time formulation of special relativity, which you are. And in fact, he goes on to use diagrams which he refers to as space-time diagrams, which is it's straight out of a physics textbook. It's fascinating. But the thing that he does that's become commoditized and helps us is that it is possible to create, and Martin refers to this in his book, the idea of what's known as a Lamport clock or a Lamport timestamp. The idea that you can actually establish an ordering in a system without actually using real time, that you can actually use a logical timestamp. You can actually use this to synchronize clocks as well, by the way, so clocks as synchronized by NTP tend to be pretty good, but the idea is you don't need to rely on that. you can actually establish a guaranteed partial ordering of events in a system by using logical timestamps. And one thing we know from a causal relationship, send happens before receive. Okay? We're not dealing with time travel. That's a different talk, which I am going to write in the future and deliver in the past. And I've already delivered it. It was really good. The sender uses a local counter. Every time something internal happens, they increment it. And then what they do is they say, hey, here's my message. And by the way, here's my timestamp. On the receiver side, we receive the message, but we also receive the request time. And we also have our own local time. And we work out which is the maximum of these two, and then we add one to it, and that becomes our local time. And this allows you to actually establish a partial ordering of all events in a network. This is really quite neat. It's quite simple as a result, but it takes a while to get your head around it. But we are coming to the end of our adventure. The whole point about a lot of this, as Lamport highlights, the concept of time is fundamental to our way of thinking. We have so many defaults about it that when we read code, we read it down the page. That means sequence. Statement followed by another statement means sequence unless there's something in between them that causes a branch, for example, or a repetition. It's implicit in the way that we look at stuff. But here, the minute we introduce a spatial separation, that takes time. And it turns out that messes with our understanding of time. Latency, failure, all of these things mess with us. And so what we try and do is reclaim it through our architectures, but also to understand the theory behind it. But I'm going to leave the last word to Douglas Adams, because it's worth pointing out, although it's very important to us, it is an illusion. Lunchtime doubly so. Thank you very much.